Hi, I am Ahmed Dawood, and today we will see how we can find out the best fit line. Okay, so before going to in the detail of how or what algorithm we can use to find best fit line, I want to give you an the idea how ML engineer thinks. Okay, and how the algorithm works actually. Okay, then we will move on the part of how we can find out the best fit line. So first of all, like you are on the way of ML engineer and you have this data set and this problem statement. The problem statement is a design such a model that can predict or estimate the price of a house by giving the area of a house as an input to the model. Okay, so this problem statement you have and this data set you have. In the data set you have area as an independent variable, price as a dependent variable. Now you have analyzed the data and you have used some techniques, some EDA, some techniques on this data set, and you have figured out these the independent variable or independent variables, if there are multiple, have some linear relation with the price variable, which is dependent variable. You have figured out that by using some graphs, some like a scatter plot, etc. Now you go towards the part of model selection and you have selected the, let's suppose for now you have selected the linear regression as your model. Okay, now you have selected the linear regression as your model. Here you have selected the model. Now your training phase will start. In the training phase you will have a data, and this is linear regression model. When you're using or doing coding, in next sessions we will do that. You are using some libraries like scikit-learn library and linear model, linear regression from the scikit-learn. It will be very easy to import the library, to use the library. But how library is actually working, it's really important to get a concept. Okay, so here you can see this is a linear regression model, and what is linear regression model? It's nothing but a linear line. Okay, here this one is a linear line. Y cap is equal mx plus c. During the training process, you cannot do prediction before. Uh, First, you have to train your model, then you can do or go for the prediction. Or in other words, you can say first you have to find out best fit line, then you can go towards the part of prediction. Now you have this line, this equation of line, which is y cap m x plus c. Okay. Now here, this equation of line is mxn plus c. Now you have to find out the parameters of the line for the best fit line. So let's say these are the parameters of best fit line m and c. Now you have to find out what will be the parameters M and C for the best fit line. If you can find out M and C, you can find out best fit line, because let's say you have find out M is equal to C is equal to 3. Your equation automatically will become y cap is equal to x plus 3. Okay, x you have. Now you will put the value of x, you can get the prediction. Okay, now the main part is to find out these parameters M and C. Okay, how you can find out, we will do that today. Okay, now you have such a graph, scatter points here, and you don't have any model here. You are doing or you are in the training phase. Let's say you have find out your parameters m and c. uh, Here like m, you have find out m is equal 0.13. Okay, you have find out m is equal 0.13, and you have find out your c is 1.8. Okay, you have find the parameters for your best fit line. Now you can say your model is trained, or you can say your training part is completed. Now you can do go for the prediction. Now let's say you have a, here you have a area 34 and you want what will be the price of if the area will be 34. You are interested in to calculate or to get the prediction or estimate for that price. What actually you will do, you will pass this 34 to this model. Okay, model actually do, model have this equation in it, in which it has find out these m and c. Now it simply pass here in the place of x, it pass the value of x which will be 34, then multiply this 34 with the m 0.13 plus 1.8, and it will get or your model will get 6.22, or you can say y cap is 6.22. You can say this is the prediction, this y cap is prediction, or you can say model has predicted that the price for the area 34 is 6.22. Okay, in this way your model or your machine learning process works. First you have to train your model. During training of your model you are actually finding some parameters. What type of what parameters? We can say that best parameters. Okay, after the part of training we can say we have find out our parameters, then we can go for the part of prediction. Now I will come back to towards the today's session, how we can find out our best parameters like here m and c. Now we are interested how we can find out these m and c, or you can say best fit line. The first algorithm that we will see, it's a gradient descent, and it's very famous algorithm in the lot of in the neural networks and deep learning part. This gradient descent has a lot of importance and it's lot in use. Now keep in mind there will be a lot of maths I will use here. Don't confuse with math. Just get the concept, how maths involved in it, and what's going on behind the concept. Okay, what's going on behind the training part. Okay, now it's up to you. You if you want to go in detail of maths, you can go. If you are not uh, really comfortable with the maths, it's nothing big deal. You just take the concept. Okay, so come back towards our today's session. So here I have told you, today we will see the gradient descent algorithm, and this gradient descent algorithm will help us to find out the best field line. Okay. Now, in the last session, we have seen that our error is, uh, let's say it's E1, it's a actual minus prediction. Okay. We already know this one. If I will write in this way, actual will be my Y1 and the prediction my y cap 1. Okay, I can say in this way. So this is simple as that. Now this is sum of squared error. I have written it in this way, y1 minus y cap 1 square. If there are n points, then up to so on yn. Okay, now sum of squared error you can write in this way. If I will zoom here. Okay, now you can see, you can write this in the way of sigma I is equal to 1 to n, means you are adding these terms, these squared errors, and here yi which is actual and y cap which is prediction. Now what is this y cap? This y cap is mx plus c. Okay, if this is yi, then here you can say m which will be slope, c will be intercept, and keep in mind like here you have these points, this is your line. Now this line will have the same slope and same intercept for all the points. Okay, as your x is changing, your y will be changing. So m and c are not like in this way, I is equal to 1 to m and c will remain same. Now for you to give you an idea what actually m and c, m as I told you, m is a slope and c is the intercept. Okay, these are some mathematical terms. Actually we usually call the intercept this point. Okay, if I will use here this one. Okay, So we usually call this slope this one. Where our line is cutting the y-axis, we call it as a slope or intercept, sorry. So we usually call intercept this one, okay? And what is slope? Slope is angle, angle with the x-axis, okay? So here I can say this is the angle. We usually m is also equal to tan theta, and what angle this line have with the x-axis, let's say here the 30-degree angle. So the tan of 30-degree will be your slope, okay? These are just technical terms. So your m and c, you are interested in to find these m and c. If you can find out that m and c, you can find out your line. If you are you can find out m and c for the best fit line, you can find out your best fit line. Now I am just replacing this y cap with mx plus c. Due to this negative sign, here I have gotten this negative. Okay. Now here SSE, which is sum of squared error. Here you already know yi, which is your price. This data you have already. X you already have. You don't have M and C and also SSE. Okay, these are the as your M and C's are changing, your line is changing. As your line is changing, your sum squared error is changing. Now you got a function of M and C in the form of sum squared error M and C. Here this is your function yi minus mx minus c. Now you have to find such a M and C which is minimum sum of squared error. Here let's say you are plotting your SSE, okay, with respect to M and C. Let's say here if I will draw in this way, M on the x-axis, let's say, as there are three variables here, so that's why there will be three dimensions. M on the x-axis, C on the y-axis, and SSE will be on your z-axis. Okay, if you will plot a graph of this function that we have here, it will be like this, like a parabola. Okay, so I have this function exactly here. You can see here. Now axis E you're on the z-axis, C is on your here. If you will see, C is your C is on the y-axis and M is on the x-axis. This function you have, and you can see that this function is like a ball. Okay, this function is like a ball which is three-dimensional ball. Okay, this is like a three. Now, as you can see, SSE on this side. Okay, and on the, or you can say SSE is on the z-axis. Now you can see here your SSE is minimum at this point. Now what will be your M and C at this point? You are interested in it. Okay. As your SSE is minimum here, your SSE is minimum where at the you can say lower part of the your ball function, your SSE is minimum here, and what will be the M and C at this position? Okay, when you will see in the form of three-dimensional space, you can analyze in the three-dimensional what will be M and C when your SSE will be minimum. Okay, now we have to find out that. So how gradient descent approach works? From the gradient actually mean we usually call gradient, you can consider is a direction, you can say it, and the, or you can say the slope. Okay, you can say that descent is going downward. Okay, going downward. And how this algorithm works, there is a good example here I mentioned. Suppose you are lost in the mountains in a dense fog, and you can only feel the slope of the ground below your feet. Now, how you can go towards the to the ground? A good strategy is to get to the bottom of the valley quickly, is to go downhill in the direction of the steepest slope. Okay, you are feeling by using your footstep where the slope is steepest, and you will move in that direction. This is exactly what gradient descent does. It measures the local gradient of the error function. This is your error function. Here I am saying SSE is an error function. So this is it measures the local gradient of error function with regards to the parameter vector theta. Like here theta we have here m and c. Okay, so we have two parameters here, and goes in the direction of descending gradient. We are going in the direction of descending gradient. Once a gradient is zero, you have reached a minimum. Here you can see at this position our gradient, as I am saying you, gradient is such a slope. So it's if your it is SSE on the z-axis, you can see here your slope is zero, or you can say your slope has angle with the x-axis and y-axis. If here will be y-axis, your slope has a zero angle with that. Okay, like here you can say there is a 0 degree angle here. Or if two dimensional, you can easily understand at this position. If you will take a slope, this slope and this line, this x-axis have a angle 0. Okay, so that's why it is saying. Now we have to move at the position where SSE has a slope 0. How you can go that? Okay, first keep in mind, if you cannot calculate the derivatives, so you can refer to some other resources to find out how we can calculate the derivative and what is actually the concept of derivative or gradient. You can see that video of a very good one I have find out for you. This one on the three blue one brown channel. You can see this video derivative, the paradox of derivative. It can give you a concept how derivative actually works. Okay, how derivative is nothing but a rate of change. Like if here the ds over dt, you can say how much ds is change, how much ds is changing with respect to change in t. Okay, how much this ds is changing. Okay, how much ds is changing if you are changing your dt. It's actually the concept of derivative. Now here, how gradient descent works. First, you have to initialize your parameters. Like here the parameter are m and c, some random initialization. Okay, then you have to calculate the partial derivative of the cost function with respect to each parameter. Like here your cost function is SSE. You can say it as SSE as a cost function, as an error function, as a loss function. It's not a big deal. It's up to you. Okay. Then first you have to calculate the partial derivatives with respect to, like partial derivative of SSE with respect to M, with respect to, then partial derivative of SSE with respect to C. Then update the parameters, update the M and C that you have randomly initialized here. Update your parameters M and C, update your parameters M and C in the opposite direction of gradients. Okay. Here I am using here a formula. It automatically uh, can do that the opposite direction. Okay. This part. Now you have to repeat the step 2 and 3 and till the maximum iteration reached, or you can say minimal cost function value achieved. Each time when you are updating your parameters M and C, you are calculating your SSE accordingly. Let's say you have started from here. Okay, You have randomly initialized M and C and you are reached here. Now you calculate SSE, then you will take a partial derivatives. Partial derivative actually give you a direction. You move in that direction, in that direction, in that direction, and in when each time you are updating your parameters, you are also calculating SSE until you will reach your minimum SSE. Now, how you can find out that this SSE is your minimum? When your SSE is decreasing and suddenly start to increasing, or you can say if your SSE decreasing here and suddenly cause to increasing. Okay, when there is sudden change from increasing to decreasing or decreasing to increasing, then we can say at that point you can say your SSE is minimum. Okay, in this way you can do that. So that's why they are mentioned at the minimum cost function value achieved. Now, how practically you can do that? Initialize M and C. Let's say you are initializing M and C by a value random value 1. Now you are calculating your equation y cap. You are just passing your 1 and M and C. Now here by using value of x that you have in your data, here you have in your data, you are calculating your SSE. You have x and y. You just pass here y. This is y. This is y cap. You have pass here x value of x and here M and C, and you can calculate the SSE. Okay. Now you will take a partial derivatives of SSE with respect to M, SSE with respect to C. Partial derivative with respect to M, you will get this one. Okay. Uh, I think you don't need to go in detail of how you can achieve uh, these values or these derivation. If you know about the how to calculate the derivative, maybe you can easily figure out how this I have got here. Okay. So now second, you will calculate SSC with respect to parameter C. Okay. Now you will here as I have calculated here. Now you have to pass the values here, like here. Uh, xi, yi in case of m, you are passing here, you can calculate it by like here xi, yi. I have calculated here. This is xi, yi. This one is xi by I, and their addition is 1042.5 uh, xi by I. But here I have yeah, this one is 1042.5. Okay, so in this way you can calculate the values here. M and C you have randomly initialized 1 1, and you can get your SSE with respect to M, which is this one 9235. Okay, now in the same way you can calculate for the with respect to C. Okay, you have randomly initialized M and C randomly, like I have randomly choose here M is equal to 1 and C is equal to 1. Then you have taken derivative of SSE function with respect to M and C. Okay, now you have gotten these values, these derivatives. Now the third step here is to update the parameters in the opposite direction. Here you are updating your parameter. This is your previous one, which is 1. M is equal to 1, that you have previously chosen here randomly, that first time you have chosen here minus alpha. I will tell you what is alpha, and here you have passed partial derivative with respect to M, and you can get a new value of M. In the same way, you can get the new value of C. Now, what is here alpha? Alpha is a learning rate. Learning rate. Okay. If I will draw here, like this is a function here. Okay. This is a function. Now you are moving in the direction where the SSE is minimum. Okay. This is SSE is minimum. You are moving in that direction. Okay. Now, how bigger you are taking the concept? Like here, you have taken the step this one, this one, this one, this one. How bigger the step you are taking, it's a learning rate. Okay. Or you can say how much you are changing your M at each iteration of algorithm. Okay, how much you are changing in the M. If you are changing in your M, like this is M at the first iteration and this is M at the 10th iteration. Okay, or you can say this is M at the second iteration and then after so on. How much you are changing your M, and in each iteration you can say it's a learning rate or you can say step size. Okay, so we have to use the optimize step size so that we don't pass out this our minimum point. Like here, if you are at this position, you have, if your learning rate is very high, you can jump that your minimum point. If your learning rate is very low, then you are moving, your training will be very slow. Okay, so don't get confused how you can get your optimized learning rate. It's a part we will see in the neural network, maybe in more detail. But the whole part, the libraries or the modules that we will import in the code can do by itself. But here, just take the concept. Okay, what is learning rate? Here you can see this is the learning rate alpha, and I have used here, let's say I have used here 0.0001. Okay, now I have this one that I have randomly initialized. This is learning rate that I have chosen. This is partial derivative that I have calculated. Now my M is 0.0765 and my C is equal this one. Now again you have to calculate the partial derivatives. Again you have to calculate these partial derivatives for both parameters. Again you have to subtract, like next time you will subtract, your M will be in this way 0.0765 minus your alpha, which will be a 0.0001, and here you will again calculate the partial derivative. Again you will update your M, and in the same way you will update your C. Okay, the process will be continue until you will get your optimized M and C. And I have told you how you can analyze that you have reached your optimal M and C. Like if you, when you have crossed your minimum point and suddenly your SSE goes to increasing or decreasing, then you can say that you have reached your optimal M and C. Okay. Uh, in the simple way, I can say this is a U-shaped curve, and here SSE you can say on the Z-axis. When you are moving in the direction, your SSE is decreasing. Okay, and you are decreasing your SSE, suddenly SSE cars to increasing. Okay, you are increasing your parameters here. You find out, you are finding at each iteration what is your SSE, what is your SSE. Let's say your SSE first time was a 500, then 400, then 300, then 100. Then suddenly your SSE again cars to increase. Okay, then you can say the parameters at this position will be your optimized parameters. Okay, in this way you stop your algorithm. Okay, this is one way. You can also stop the algorithm in this way, that your maximum iteration you can limit out. Like you have to iterate your algorithm 100 times only. Okay, it will stop automatically after the iteration 100 times. It will update your parameter M and C, then it will stop. Now by repeating this process you have find out your optimal parameters, which are here: M is equal 0.1358 and C is equal 1.80, and these are the at the minimum SSE position. Okay, now you can say these parameters by the line of these parameters. Okay, like this line 0.1358 x plus 1.806, it's a best fit line, it has lowest L. Okay, now you can say that your model is trained. Okay, now you can pass the value of x here and you can go for the prediction. Okay, so this is a gradient descent, a lot of maths involved here. if you know about the how to calculate the derivatives, partial derivatives, and you can also maybe get if someone from you have a knowledge how to calculate the derivative, maybe it will be easy for him or her. But here there is this session is not for you to confuse with the maths, just to take the concept how maths involved in it. Okay, how the process of training going on. Okay, there is not a magic behind it. There are some mathematical techniques. Okay, again, just a quick revise. You have find out your sum of squared error. Okay, when you have find out your sum of squared error here. Okay, here you when you have passed your y cap equation, which is equation of line, you have passed here the parameters m and c. Okay, now your sse becomes a function of m and c. Okay, now you have to find out the m and c where sse is minimum. Okay, you have this type of graph, parabola type graph. You run the gradient descent algorithm. How gradient descent algorithm works? It take at the start it choose the randomly m and c, the value for the m and c. Then it calculate the sse by having that m and c. Then calculate the partial derivative with respect to m and c of sse. Then update the parameter m and c. Then again the process will repeat until we get our optimized m and c. Okay. In this way, gradient descent works. After the algorithm run and reach to the position of minimum error, then you can see your model is trained here, and you have find out your optimal parameters. Now you can go for the process of for the phase of testing the model, or you can say for the phase of deployment of the model or prediction of the model. Okay, so I hope you got enough for today. But it is really I hope this will be really interesting for you. Again, don't confuse with maths. Just take the concept. When we will do coding, the whole process will be just you will do in this way. You will import sklearn dot linear model dot linear regression. Okay, you will import this model here, and simply you will do like this is your model is equal to linear regression. Okay, this is linear regression. Simply you have to do model dot fit, and here you have to pass the your data. Okay, x and y. This piece of code can do all the stuff, all the maths. Okay, actually this fit function done the part of training, and you can say here this fit function can do the training part, and here the process of gradient descent involved. Okay, don't confuse that when we will do coding, it will be very easy for you. But here the aim is to give you the concept. So I hope you learn a lot. So for now, thank you.